My name's Alan Champneys, as our host just said. I'm a professor of applied nonlinear mathematics, and I'll explain what nonlinear means in the course of this lecture in the Department of Engineering Maths at the University of Bristol, but I also have a job as head of the Queen's School of Engineering, again, whatever that means. So what is the title of this lecture? It's a play on words, familiarity breeds contempt, and actually I didn't come up with this title. It was Nick Trevethan, who's a professor of numerical methods at the University of Oxford. And what I want to get across is the notion of nonlinear science, which you sometimes hear in the media, notions of complexity, notions of emergence, chaos theory, or whatever. And what do we, some people in social sciences, etc., talk about nonlinear thinking or whatever. What do people mean by that? And I want to contrast that with the linear view of the world. And this is in an engineering faculty, so most of my examples will be from engineering. Okay. You'll see these busy slides, but I'm going to speak to them for quite a while. So first of all, what does linear refer to? Linear refers to a line. In this case, we mean a straight line. And actually, linear is usually referring to some kind of input-output relationship. We're familiar with this when we do physics at school. It's called Hooke's law. Robert Hooke, great empiricist. Did loads and loads of experiments. Essentially, the extension of a spring is approximately proportional to the amount of force you apply. You apply twice the force, you get twice the extension. That's Hooke's law. So force is proportional to extension. You get a straight line graph, if you like. In electrical engineering, we're so familiar with Ohm's law that voltage is proportional to current and resistance is the constant of proportionality. And so you double the voltage, you double the current for the same circuit with the same resistor. In economics is driven by all kinds of linear relationship. There's something, for example, called Ocken's law that says gross domestic product is inversely proportional to unemployment. So essentially, the more people in work, the more money a country will make. Love, etc. You know, there's this belief in human relationships. The more we put into our relationship, the more we will get out. There's this view of sort of social dynamics that the more I try and convince you, the more likely you're going to agree with me. Now, I'm beginning to say some things which perhaps you realize might not be how the world works. But this is the linear view of the world. It's the one we're brought up on, and it's hardwired into us. It's hardwired into the idea of extrapolation. This worked last time, so I'll do a bit more. I'll put a bit more effort in that direction. A classic example of the failure of extrapolation was the so-called Tacoma Narrows suspension bridge in Washington State, which in the 1940s or 50s, I'm sorry, I forget the date, failed spectacularly with massive oscillations. Now, there's all kinds of theories as to what happened, but basically what happened was this. It was in the fairly early days of suspension bridges, spans were getting longer and longer, and designers realized that the more flexible you made the bridge, the better. The more resilient. You know, the principle that a blade of grass is far more resilient than a tree. A blade of grass is stronger because if in a heavy storm, no blades of grass are uprooted. They're very flexible. And so if you looked at the Tacoma Narrows Bridge and you plotted its flexibility on some graph, you'll see that it's actually twice as flexible as any other suspension bridge. So the notion of saying, well, we made one a little bit more flexible last time, it gave us a better outcome, so we'll make this one even more flexible and we'll get an even better outcome. That's linear thinking. That's just following the straight line graph and saying we're going to get double the output if we put double the input. So we can generalize that, and in maths we'd say y equals ax plus b. Now I ought to say something about equations. This is a popular lecture, and my former mentor and colleague and now Pro-Vice-Chancellor of this university, Nick Leven, told me, and I believe him actually, despite my background in mathematics, I agree with him, that you ought to be able to convince any audience of any truth without using equations. And that actually any speaker should be able to give a technical talk without the use of equations, but the speaker is allowed one equation. Okay, there's two here. I apologize, but it's really the same equation rearranged, but only if the speaker is wearing a tie. Okay, that's his rule. So you may not understand, but I've actually, about my person, got concealed a tie. So I hope you'll forgive me the one equation on this slide. But essentially, it's just the straight line graph. Y is ax plus b. And sometimes if we're looking for the solution, if this is our mathematical model, and we want to say, where is y equal to 0, and actually I've changed the sign of b in this equation here, then actually we're looking for an intercept, and what we're trying to do is solve ax equals b. And actually, I claim that the vast majority of science and engineering, the classical science and engineering, is built up on ax equals b. What do I mean by that? I'm thinking as A is my system. That's the property of the world. That's my Hooke's constant. That's a property of the plant or the system. X is the thing I want to find. That's the output. That's the extension of the spring. And B is the input. That's the force. So I've got an equation that has an input, an output, and a plant or a system. And how do I solve it? Well, it's trivial. Divide by A. Duh. Right? And I claim that is the linear world in a nutshell. Find the system, invert it, or in this case, divide by it, and we just say that the output is the input divided by the system. Okay, so, oh dear, there's more equations. Whoops. Hang on. Yep, got another tie in there. And actually, I've got two more, and then this will be the last slide of equations, I promise. So just bear with me a second. There we go. Right, so after this, it'll all be qualitative, and there are no more ties, because it would get embarrassing if I had to find some more. Or rather, I should say, even more embarrassing. So we generalize that. It's not usual that we have a system that can just be described by one constant. In the engineering world, we quite often use computational fluid dynamics, finite elements, big data. And what we do is we shove them all in a huge array or vector. It may be, of size 3, it may be of size 50, it may be of size 50 million, 50 billion in the case of really high-end computational fluid dynamics, possibly. These are our unknowns. And then we characterize the system. Sometimes we call it the stiffness matrix. Or we discretize the Navier-Stokes equations and we put it in a huge matrix, which is an array of coefficients. And we end up with something that again reads, we have some inputs, these may be forces, for example, and we're trying to find deflections, x, and A is this huge stiffness matrix, let's call it. And again, this is ax equals b. And what do? You divide by A. Trivial. Okay, there's some computational issues and you can't divide by a matrix. What you actually have to do is you have to multiply by the inverse of the matrix, which is what I've written down here. X is A inverse times B, and that means something non-trivial, and actually you never solve it like that. You solve it using Gaussian elimination or iterative methods or something. But conceptually, it's trivial. And conceptually, if I double the input, I double the output. If I put two different inputs in and add them together, I can add the two outputs together. That's the linear world, the world of proportionality. It's true in other spheres, not just algebraic equations. If I have differential equations, linear vibration theory, for example, would have this D here is called a linear operator, and that linear operator, actually I've changed notation to L at this point, would be given something like this. We can have partial differential equations for the wave equation. That would be another differential operator, etc. But in all cases, what do? We just multiply the input by the inverse of the operator, whatever that means. Okay, that's techie. It involves big computer programs sometimes. But conceptually, it's the same. Ax equals b, divide by A. And we get this property that you get from a straight line graph, that a change in the output is proportional to the change in the input. Put in twice as much work, you get twice as much out. But, okay, now I'm going to give you an example. Okay, this is something we teach maybe third-year undergraduates, vibration theory. Vibration theory works like this. Here's my drawing of a helicopter, and what do? Well, we want to measure the vibration modes of this helicopter. We want to know, what is this helicopter going to do in flight? So what do? We put it in the lab, and in fact, just across the corridor from here, we have a dynamics lab at Bristol. We have precisely this experiment. What are they doing on that experiment? Well, essentially, they're shaking the helicopter. They're playing in some kind of random excitation, some kind of shuggling about of this helicopter. And the output from that gives you a signature of the system that tells you about all its vibration modes when the thing is in flight. Just one test. And that works only if the system is behaving linearly. It uses the assumption of linearity, and it uses it like this. There's a very clever idea called the Fourier transform that basically says we take this chaotic signal or this random signal, this noise that we're shaking the helicopter with, and we say, what frequencies are there in there? This is called the Fourier transform. You break something down into its frequency components individually. And then you work out the response of each frequency, the response of the structure to each individual frequency in this Fourier world after doing this strange transformation. Again, it's just a black box on a computer on MATLAB, which many of our students here use. It's called FFT, the fast Fourier transform. And there's even something called FFTW, which is called the fastest Fourier transform in the West, which basically can take any signal and turn it into frequencies like that, fast in the blink of the eye, and do this transformation and this analysis exceptionally quickly. This all relies on linearity, and basically you can characterize the system as something called a transfer function, and you can characterize in this world of frequencies of saying, if I play in frequency 1 plus frequency 2, I'm going to get the output from frequency 1 plus the output from frequency 2. That's the linear world. And you find amplitude independence as well. You find if I play in twice the amplitude of the thing at frequency 1, plus 7 times the amplitude of the thing at frequency 2, then I'm going to get an output that's twice the output of the first frequency, plus 7 times the amplitude of the other. The fundamental structure just scales with the size of the signal I put in. This is linearity. It's all across engineering. Now, I'm not trying to diss linearity. I'm not trying to say that linearity is something that gets aeroplanes in the air. Linearity is very good for understanding about stability. What is stability? Stability is saying, I've got a system, it works. I'm going to poke it slightly. I'm going to make a small change. Linearity is very good when you're talking about small changes. That's essentially because every graph that's sufficiently smooth that you draw, if you zoom right in, locally it always looks like a straight line. And that property is used again and again and again in engineering. We talk about operating points. If you're close to an operating point, provided your system is well defined and nice and smooth near that operating point and no physics changes, then you're going to get something that locally, close to that operating point, looks like a straight line. Okay, so this is a good principle for designing things, not dissing nonlinearity, but I claim the real world isn't like that. And for the rest of this lecture, I want to show you some things that go wrong when you look at the real world that has nonlinear relationships. And I'm going to, in this talk about 3 different kinds of nonlinearity, if you like. There's what I call weak nonlinearity. This is sort of mildly non-Hookean springs, that you get sort of slight softening. It's not quite a straight line, it's locally a straight line, but it changes a little bit. Then we're going to have strong nonlinearity, where essentially in the operating region, in the region that we're interested in, we've got something that's nothing like a straight line. And then the most catastrophic, the most unlike a linear system, are non-smooth or discontinuous nonlinearities, where you get jumps or corners. And actually the real world is like that. We have switches, we have hard contacts, etc. in all of our systems. We have changes of zone. In physics, they're often called phase transitions. They abound in the real world. So I'm going to have 1, 2, 3, 4, 5, 6 slides from now on, and each is going to give you a different hallmark of nonlinearity, a different thing that if you see it in your system or in the real world in data, you say, that's that. I see. That's because the system is really highly nonlinear. So I'm going to talk about excitability and threshold behavior. That breaks amplitude dependence. It completely throws it, this amplitude independence. Putting in twice as much does not give you twice the outcome. I'm going to show you that the dynamics from certain inputs can be completely chaotic. They needn't be regular, from very simple systems. I'm going to talk about tipping points or bifurcations. I'm going to talk about systems which, when you drive them a little bit harder, naturally start to oscillate. I'm going to talk about discontinuous things and non-smooth things, and I'll say just a little bit about spatiotemporal localization. So these are just flavors. So here's my first thing. My first thing is excitability. It's the property of a living system, not necessarily living actually, it can occur in engineered systems too, to respond strongly to the action of a relatively weak stimulus. So the classic example of this are nerve fibers, heart tissues, and muscles. You think of what a neuron does. A neuron basically integrates from its environment. It's constantly, through its dendrites, listening to hundreds, maybe thousands of other neurons. And if the inputs are sufficiently synchronous so that at some time the internal voltage goes above, or the current perhaps goes above, or maybe certain ion channels goes above a certain threshold, suddenly the neuron fires. Heart tissue is the same. Under electrical stimulus it does almost nothing and then beats. So if you want to understand excitability, actually the word is extremely well defined because of its other context. And I think of it as like the psychology of a teenager. I'm going to use the name of a random person who may or may not be my middle son. So I can think of a typical conversation in our house which might go something like this. Dominic, could you go and tidy your room, please? Nothing. No response. Dominic, could you please go and tidy your room? Nothing. Dominic, please tidy your room now. Dad, you... I won't swear. Somebody's holding at the back there, I should tell the audience, a big thing that says, do not swear, Alan. So I won't. But anyway, there's a certain amount of shouting and an awful lot of really unpleasant things. Many hours later, the response finally, as he tidies his room and he comes downstairs and says, sorry, Dad. So that's excitability. It's thresholding. Once you go over a threshold, you get an extreme response. Somebody also described it to me as this is Bart Ehrmantraut's idea of, who's a fantastic guy in neurodynamics and math biology generally, definition of excitability. He says it's like the dynamics of a toilet. So I don't know if you think of an old-fashioned toilet with one of those chains. If you pull the chain slowly, nothing happens. You just get this blub. A little bit of water may come out. You pull it slightly harder, tiny bit more water comes out. Blub, blub, blub. So you pull it harder still, and then suddenly the thing flushes, the cistern empties, the system eventually settles back down to equilibrium. And during the time until it settles back down to equilibrium, it's not responsive to another pull at all. That's exactly how neurons and heart tissue work. That's excitability. And it's a highly nonlinear, it's a strongly nonlinear effect. Then there's chaotic dynamics. This is a simple pendulum. The amplitude is approximately independent of the angle of swing, only approximately. And what this guy now does is he attaches a second pendulum, or actually he unscrews the two bottom pendula, which were rigidly attached. Look at that motion. It looks like it's random. Look at that lower pendulum, the way it dances about. It looks, to all intents and purposes, as if there's random effects going on, and yet, to very good approximation, this is the equations of motion that you would get from Lagrangian mechanics or Newtonian mechanics or whatever. You know, Newton could, in principle, write down very accurately the equations of motion. The history of this, which is a very simple system, which we've only made moderately more complicated in the single pendulum. Single pendulums are so regular that they're used in clocks. Actually, it's kind of interesting because the reason why a pendulum is used in a clock is they tend to have very low damping, so you don't need much power to make the thing go, and the period of the swing is approximately independent of its amplitude. And that's true as long as the pendulum is only swinging by a few degrees. It's completely false if you allow the pendulum arm to almost go over the top. And actually, pendulum clocks, typically, they actually have a sort of non-smooth element in that they have some little stopper that the pendulum is required to hit, and that gives the pendulum just a tiny bit of force. Historically, they were done by a sort of a pulleys and weights system, such a tiny little piece of force. Sometimes it's done at the top via a gearing system, that's called escapement, that enables the pendulum just to keep going regularly. All we've done here is change that slightly by adding a second pendulum, not changed the laws of physics, not gone to a parallel universe. We have very straightforward laws of physics that are approximately applying here, and yet we get this pseudo-random kind of output. So we've changed the system slightly, we get a completely different kind of output. Moreover, we have sensitive dependence on initial conditions. You can trawl all over the internet and you see these butterfly-shaped objects. These are called strange attractors, or the Lorentz attractor. And this is historically very important in the history of chaotic dynamics, in the history of nonlinear science. Ed Lorentz was a weather forecaster. And in the 1960s, there were sort of two schools of thought in weather forecasting. The dominant school of thought was about pattern matching, as we'd now call it. Namely, we've seen one of these weather patterns before. Statistically, when we've seen one of these weather patterns, normally what happens is one of those. And there was something called synoptic weather forecasting that was basically entirely statistical. It was really early days. There was a belief that you would never actually forecast weather based on the laws of physics. It's just way too complex. And what Ed Lorentz discovered is now called the butterfly effect, which is a kind of play on words, because in the right perspective, that object there, that mathematical object, looks a bit like a butterfly. But the way that he rationalized it and reasoned it was that a butterfly flapping its wings today in Bristol could, in principle, change the weather in Santiago, Chile, in 6 months' time from a snowstorm to bright sunshine. That you get this tiny sensitive dependence on initial conditions. Now, what is this a picture of? Well, what Ed Lorentz did is he took something that represents a very, very simple weather feature, namely a single convection roll. So sometimes on a certain day, you get these clouds which involve hot air rising, cooling down, and then coming down again. So he just looked at a system where the roll could go to the left, it could go to the right, or you could have pure conduction. And he basically reduced this reductio ad absurdum to a ridiculously simple set of differential equations that probably has nothing to do with the weather whatsoever. But essentially, his reasoning was, if I can simplify the system and still find in the huge simplification of my system complicated things, then maybe the real thing is also complicated. And he set this thing running on the computer. And these were real computers. This was one of the first computers in the US, a Royal McBee in 1962, and found that he ran the code, and it took overnight just to sort of simulate for a few minutes, and he found these swirling patterns, sometimes to the left, sometimes to the right, as we plot here. And then one time he thought, oh, that was interesting. I'll try and restart the computer from where I left off last time. But he was only storing 4 or 5 digits. And as he typed in the 4 or 5 digits, the thing did something completely different. Rather like the pendulum, it swung to the left several times, and then suddenly it went over the top and did something completely different than last time, where it kept swinging to the left. And he had these two trajectories, as we call them, these two futures, these two possible futures that just differed in the 5th decimal place of the amount of heating in the system, or the amount of leftwards roll or rightwards roll, and found completely different outcomes. And that he called sensitive dependence on initial condition. There's a lot of stuff written on chaotic dynamics, which I won't have time to go into today, but this notion of something that looks pseudo-random, but is actually deterministic. It's given by the laws of physics that you can write down. There is no random effects going on, and yet it has this notion of sensitive dependence of initial conditions. And I think football is the perfect example of sensitive dependence on initial conditions, because I'm going to look really stupid now if I make predictions, because most people watching this, the World Cup will have already happened. Now, I'm just imagining a couple of possible futures. On Saturday evening, our time, England play Italy. And I noticed there's some Italians in the audience, and Italy are well known for their attacking flair and winning by many goals. The typical scoreline in an Italy game would be 10-0 or 10-7 or something, because they're used as a defence. No, that's not true. And England, of course, are really good at being consistent. They always perform well. They always do well when they're predicted to do well, which is also not true. So what might happen? So the England hero is Wayne Rooney. Now, I want you to imagine England versus Italy. It's in the first half, perhaps. Rooney has a shot on goal. Now, just imagine what might happen if that shot just catches the post, the post of the goal, and deflects inwards and it scores, what would happen? Well, firstly, Rooney would feel enlivened, would feel confident, would feel good about himself. He might go on to score more goals in that game. He might go on to win the Golden Boot. He's a very talented player when he's confident. England might win that game against Italy. They might go forward from the group stage. They might even reach later stages of the competition. What's certain is they'll go out to a penalty shootout. That actually doesn't require any prediction whatsoever, because that always happens. But suppose now instead the ball hits the outside of the post and misses. Then it's a goal kick. The goalie might boot the ball down the other end. Pirlo or whatever might get a lucky deflection, and Balotelli knocks it in. Italy are 1-0 up. Rooney feels deflected, Rooney dejected. He thinks, what if I'd scored that goal? Oh my goodness, he gets more and more anxious. He starts playing badly. He puts in a rash tackle, gets sent off, and that's him out of the competition. England then go on to lose their next group game and draw against some minnow team like they usually do, and they're out. The England manager is sacked. Notice what was the difference. It was millimetres between hitting the outside of the post or the inside of the post. Real life has sensitive dependence on initial conditions. There's, what's that film with Gwyneth Paltrow, Sliding Doors, that all uses this idea. It runs two parallel, it's a rom-com. It runs two parallel stories depending on, it's set in London, whether or not she made it through the closing tube doors onto the tube train, or whether or not she didn't. And it runs two futures that end up being entirely different. Same idea. Ed Lorenz was the first to notice this. Okay, I need to move on. In climate change at the moment, and in many other systems, sometimes we talk about tipping points. What's a tipping point? Well, a tipping point it's a bit like excitability, but now I'm not thinking of changing, I'm thinking of more of a steady state type situation. I'm thinking more of, suppose I had, I'm just looking here, I think I noticed earlier, except my colleague has tied it up perfectly for me, but suppose I get some long, thin object. Imagine this is a beam here. This beam can take some load. This beam will take a certain amount of load before it'll buckle, right? And that's a tipping point. Now this is a rather horrible buckle. It's sort of flipped over or whatever. But a tipping point is essentially where you've reached the point where you can no longer carry on as you did before. So we talk about this in climate change. We talk about what is the change in the North Atlantic oscillation that will lead to the death of the whales and then the melting of the ice sheet and disaster for everybody and the end of the Maldives as we know them. What is the tipping point? Well, the mathematical idea of a tipping point is a bifurcation, a qualitative change in the state, that is the output of a system, under change in its operating conditions. This is like the physicists call a phase transition. Something is going along fine, the Earth is basically adapting, bang. It seems to me that the weight of evidence is undeniable that human intervention is causing temperature rise. It doesn't seem to me that it's necessarily the case that there will be a catastrophe, that we will reach a tipping point, because what happens after the tipping point, what happens after the buckle, that proto-beam I had just fell over. It was fine, nobody died. We'll just move into a different regime, a different operating point, and these are called bifurcations. It's a property of nonlinearity. If you have linearity, if you have strict proportionality, you don't see these tipping points. You don't see these bifurcations. And then we have the notion of the onset of oscillation. Something is just sitting there, and then suddenly it starts oscillating. I had this phenomenon in my office. It's a long story which I won't go into, but this building was extended, the one we're in at the moment, and a new heating system was retrofitted because the one that was embedded into the concrete floor no longer fitted the bill. And in this retrofit system, I noticed that on particularly warm days, it took a long time to heat the system up, so generally through winter it was on every day. But if it was a mild day and people had turned their thermostats off and their radiator, I would suddenly start to hear an oscillation of the valve in my thermostat. Now, I'm actually doing research on precisely those kinds of oscillations at the moment, but it's an example of a self-excited oscillation. There was no conductor playing a certain frequency into the pipe system. The system was being actually, in this case, driven too lightly in a valve type system. If you drive flow through a valve too slowly, it's liable to this kind of oscillation. Another example, a classic example, is so-called wing flutter. Under certain flight conditions of an aircraft, under certain flight conditions, the wings are liable to flutter. And that the word is exactly what it sounds. The wings start flapping at some characteristic frequency. There's no input that's periodic, but the output is. Organ pipes, another example of things that give you a characteristic frequency, an oscillation out of a continuous input. So dynamical systems that are dynamic, that have a steady input but have an oscillatory output, the transition to that oscillatory output is known as a Hopf bifurcation, which is the sudden onset of a finite amplitude oscillation from steady state under change of its parameters. And then you can have further bifurcations. Again, I won't go into any details here, but one example of this was a dripping tap. Some slightly wacky US physicists decided to do an experiment on a dripping tap. And as they opened the tap slowly, they can make the tap go drip, 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 drip periodically. And then they slightly changed the amount to which the tap was open, and they noticed that it went drip, 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 drip. Slightly changed it again, and it went drip, 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 drip. And this is called period doubling. You go from something that repeats once every cycle to something that takes 2 cycles before it repeats to something that takes 4, 8, 16. And it was shown by Mitch Faugenbaum that this is actually some characteristic ways in which systems go from steady state to oscillation to chaotic dynamics. It's called the period doubling route to chaos. And in a very short window of time in the 1970s, the scientific community was kind of deluded that this might be an explanation of turbulence. And as turbulence is much more complicated because it's spatiotemporal. It's not just temporally chaotic, it's spatiotemporally chaotic. And here's a lovely poem I like about turbulence that says, big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So that describes the complexity both in time of things spiraling around each other, but also in spatial scales of what is fluid turbulence. Okay, almost there. I won't have time to do all of these demos. You can find on a web page, which I will show you at some later stage, the first thing I want to show you. Because the whole point of what I want to say is that we understand mechanics and dynamics very well. If I wanted to describe in computer simulation the dynamics of this ball, right? I've got a ball here, a tennis ball. I could write a really good computer simulation that would accurately determine the dynamics of this ball until it hits the floor. When it hits the floor, something bizarre is happening. If I did that perhaps not with a tennis ball, but with this board eraser, even if I spin it in the air, I could simulate that, but when it hits the floor, that will never bounce the same way twice. There's a huge nonlinearity, a whacking great nonlinearity. I'll do roughly the same thing, does something different, landed on its top. There's a huge, harsh nonlinearity, one of these sudden jumps, one of these very short timescale nonlinearities. And that's an area I do, and a number of other people at Bristol do active research on, the dynamics of non-smooth or discontinuous systems. And I want to give you one example, which is, in fact, I'll give you 2 examples of areas that we're currently looking at. One can be described as, why is it that it's easy, perhaps I'll turn the light on here for the blackboard, why is it easy to draw a line with a piece of chalk if I drag the chalk, but it's really hard to do the same thing if I try and push the chalk? Do you see what happened there? And in fact, this is a good way of drawing a dashed line if you get it right. I'm doing exactly the same thing as when I dragged the chalk, but now I'm pushing the chalk, I'm getting some kind of non-smooth oscillation. I'm getting some kind of lift-off, sticking, rotating. And this, I believe, is an example of something that's known as the Painlevé paradox, which I don't have time to go into, but Painlevé was a really interesting character, well known in physics, in mathematics, but was also Prime Minister of France twice and had to resign due to basically financial crises. If only ministers of today would do the same thing and go back to science, perhaps we'd be in a better situation. Another project we have, I showed you about bouncing balls. Generally, there's some good models for bouncing of spheres on hard surfaces. Newtonian coefficient of restitution. If I drop this ball, it'll bounce to a certain height. If I drop this basketball, it'll bounce to a certain height. This is a particularly, it's not going to be a very good demo today because this basketball is actually not very well blown up. So if I drop this, it doesn't bounce much. If I drop this, it bounces a bit more. What do you think will happen if I drop one on top of the other? Let's have a look, shall we? Whoa! Look what happened to that tennis ball. All I've done is I've dropped the tennis ball. Itself will just bounce like that. Basketball, almost, it's pretty low coefficient of restitution. I drop one on top of the other, and I've just hit the camera almost. I've just almost hit the recording equipment. And then finally, another area that I've become very interested in, and I've had a number of PhD students over the years, and I'm still interested in, is how you can have continuous causes in space, and you get a localized outcome. So here's an example of the Severn bore, which is quite near here. This is a continuous change in tidal conditions, and you get this tidal wave, this bore, that travels for up to 30 miles, that gives this transition between two different flow regimes. Why there? Why not a mile downstream or a mile upstream? Why does a continuous ramping of the strength of the tide cause that? This is a fantastic experiment. These are oscillons. This is a viscous fluid that's, think of this as a glass of milk that's been put on top of a shaker and shaken up and down. And if you're in the right parameter regime, you can, instead of seeing the whole thing go up and down, instead of seeing sort of crisscross patterns on the surface, you see these little blips, these oscillons. And they always have lives of their own, and they can slowly drift and interact with each other, almost like subatomic particles. And in fact, recently there's a beautiful experiment where you can get little drops that form and that bounce, these bouncing droplets, and they interact with each other in very strange ways. These are some experiments and some work that I did a few years ago. I didn't do the experiments. We tried to come up with a theory that turned out to be much harder than I thought it would be, in granular media. This is with David Muir Wood. What's happened here is you have a paddle in the granular medium, and you've rotated the paddle to a point where the medium can't take the stress anymore, and something happens. And what you get, instead of a uniform change in the state of stress, you see these shear bands. You see these localized lines of deformation. Why is that happening? This is a computer simulation, but this is what you also see in experiments. If you squash an elastic cylinder, if you like take a Coke can and slowly, in a controlled experimental way, crush it. So I don't mean just take the can and go like you would. And what you find with this is, this tipping point is very strange because you never reach the point at which it takes the maximum load. It always does something before that, and it tends to jump into a state of localized deformation along the axial length. The theory will tell you that there will be a dimple pattern everywhere, but actually what you see is something localized. And this is something to do with the theory. It's called a snaking mechanism that I and a number of colleagues have come up with. And this is a simulation, a bit like the simulation here of the so-called Swift-Holmberg equations that describe these localized phenomenon. Okay, I've told you an awful lot of things in almost no detail. The point I want to get across is this quote due to Stanislaw Ulam many years ago. Using a term like nonlinear science is like referring to the bulk of zoology as the study of non-elephant animals. Actually, linearity, this proportionality, is the exception. That's unusual. It's only true if you're looking at small displacements generally from some operating state. And then I've shown you 6 different hallmarks of nonlinearity, 6 different effects that you see because of nonlinearity that you don't see in the linear world. Firstly, we had excitability, or the psychology of teenagers. Then we had chaos and sensitive dependence on initial conditions, or the fickle nature of football, if you like. Then we had non-smooth behavior, rattles, bangs, or why you can't push chalk, and strange properties of ball bounces. Then we had bifurcation and tipping points, or climate catastrophes, as some people would have us believe. Self-excited oscillation, having a flutter. And then localization and their close cousins, solitary waves, which you might call bumps, blips, and bulges. Which is kind of useful because for the past too many years I've been writing a book with precisely that title that aims to be a popular science book. And as I've been saying for quite a while now, it's coming out next year. But why am I telling you this? I'm just a mathematician, right? This isn't the real world. I've been talking about the world of equations and models and simplifications, etc. I haven't included uncertainty. I haven't included what engineers like to call noise, randomness. You know, Donald Rumsfeld, the known knowns and the unknown unknowns and the known unknown known. The real world involves imperfection, unknowables. It involves people, decisions, opinions, beliefs, perspectives, profit margins, the need for you to get to your next lecture. My God, is that the time? If you really want me to explain the connection between mathematical models and the real world, that's actually quite hard. If you want any more of my random musings, you can follow me on Twitter or you can send me an email. I'd like to thank you online, and I'd like to thank you, the audience, for listening. Thank you very much.